In some systems, the cores of contracting clouds never glow with anything more than the dim light of dull brown dwarfs. Our early sun now nears a critical point. Will its internal furnace sputter and fail? Or will it breach the nuclear threshold and shine across the galaxy with all the brilliance of a true star? We are now at the most critical point in the making of our solar system. At 50 million years old, the protosun and its forming planets are barely 1% of their present age. In many systems, the central star doesn't have enough mass to fully ignite. But our sun is about to overcome that fate. It has reached the critical threshold of heat and pressure, where nuclear fusion can begin at its core. Using the same awesome energy that powers the hydrogen bomb, our sun bursts into life as a fully formed newborn star.
At about 50 million years into the life of the solar system since it first began forming, the sun goes into a different phase, burning hydrogen, actually doing nuclear fusion. At that point, the sun becomes what we think of as now a fully fledged star.
Nuclear fusion will carry the sun into the distant future. It will burn long enough to support the evolution of life on Earth, shining unceasingly for about 10 billion years. Unlike the newly nuclear sun, the rest of the solar system is far from mature. 40 million years earlier, the frozen gas giants outside the snow line ceased to grow and achieved an icy stability. But in the hot inner solar system, where gas is rare but rocks abound, chaos still reigns.
By the time that the sun has become a full-fledged star, the planets in the inner part of the solar system are still trying to grow. There are small little protoplanets that are building together, colliding, getting larger and larger, eventually to become those 4 big planets that we have in the inner solar system.
But just inside the orbit of Jupiter lies a narrow region where the smaller planetesimals rule and protoplanets are rare. This is the asteroid belt, where Jupiter stirs things up to prevent any planets from forming.
Jupiter is the largest planet, and so its gravitational influence is the greatest in the solar system. There was a point in the early solar system where Jupiter was passing through what's now the asteroid belt, pumping up the velocities of the planetesimals there, causing them to collide in a destructive manner. They blew apart. We're going to try to get a feel for what a destructive collision is like in the asteroid belt, but we can't use real rocks because they're too hard and the velocities available to us are too slow. So what we're going to do is use these special lightweight rocks, which were made for us by Ryan Johnson, a special effects artist. Ryan, can you tell us about these special lightweight simulated asteroids?
Sure. So these props that we've developed here are a foamed plaster type material that we use to simulate real rocks in movies, films, and things like that. Whenever we want something to break that looks like it's hard, this stuff breaks really easy and it crumbles. So what we've done is we've taken this same material and we've developed a much larger one we're going to use to simulate an asteroid. So we've got 2 of these, and we'll smash them together really hard, and that'll hopefully simulate the collision of an asteroid.
So what sort of speed do you think we need to smash them together so they'll break?
We just need to drop one on top of another from a reasonable height, and something like that.
Okay, let's try it. Let's drop the plum.
The distance of the drop is about 18 feet, which will give the falling asteroid a speed of 37 miles per hour.
A little bit more. Perfect. Perfect right there. Okay, Ryan, we're ready for the drop.
Okay, it's pretty windy, but we'll see how we do.
All right, that is excellent. I would say that's a success.
Thanks. Yeah, that's good.
Yeah.
It's amazing how much it's like really spread out.
Right, so in the asteroid belt, all these pieces would gravitate back together and form a rubble pile, what we would call an asteroid today.
So if they're starting to come together all the time, isn't that the same process that actually forms a planet? Why wouldn't the planet form that case?
Well, no, because then this thing gets hit again and again and again. So these things keep getting pulverized by impacts, and you're just left with little individual rubble piles rather than a complete planet.
Does this reasonably replicate what you think possibly an asteroid collision would be?
This is a pretty good analogy, in fact, because you get large pieces, you get dust, and so what we think are asteroids are basically rubble piles composed of these large pieces put together, covered then in dust. And so, yeah, I think you did a good job. This looks like the beginnings of an asteroid.
Great. Well, I'm glad it worked.
Right.
The asteroid belt isn't the only region in the emerging solar system where planets fail to form. At the outer fringes of the solar system, another ring of small objects orbits in frozen silence, the Kuiper Belt.
The Kuiper Belt is a region at and beyond the orbit of Neptune that has a whole bunch of rocky and icy objects pretty far apart from one another. Now, they were never able to coalesce to form a planet because there's just not enough of them close enough together.
50 million years after the solar system was born, both the Kuiper and the asteroid belts have 100 times more objects in them than they do today. These objects will play a monumentally destructive but vital role in the final evolution of the rocky inner planets, including the Earth. The inner planets take as much as 10 times longer to form than the giant planets outside the snow line. After 75 million years, the process is near completion. About 93 million miles from the young sun, the proto-Earth has reached planet size in a relatively stable orbit. But it has a cosmic stalker.
It's actually believed that the Earth was, in its early phase, accompanied by another planet, a protoplanet called Theia, which was actually in a similar orbit to Earth, essentially following roughly the same path.
For millions of years, the sister planets chase each other around the sun in a dangerous duet. But a clash is coming that will have immense consequences for the fate of the Earth. The making of our solar system has gone on for 80 million years since the collapse of the giant gas cloud that started the process. The inner planets have largely taken shape. But now, the Earth, which will one day harbor life, faces the potential of an early and cataclysmic death. For millions of years, Earth has been followed by the protoplanet Theia. The two bodies travel in essentially the same orbit, gradually coming closer and closer. Now, for Earth and Theia, it's crunch time.
The Earth-Theia collision early in the history of the solar system must have been a spectacular event. A Mars-sized object came in and hit Earth's side, splattering part of the crust and mantle of both objects into space, forming a ring of debris from which the moon then formed.
Having survived the cataclysm and gained a moon, the Earth settles in as one of the stable planets of the inner solar system. The drama now moves back to the gas giants, whose shifting orbits threaten to tear the solar system apart. At 500 million years old, all of the solar system's planets have been formed. But surrounded by debris in the planetary disk, they are on the move.
As waves of density are formed in the disk, the planets are almost surfing on the waves of material in the disk itself. You're really shuffling the deck completely from where planets are formed to where we finally see them.
In the early solar system, the three outermost planets as a group are closer to the sun than they are today. and Neptune's original orbit is inside that of Uranus, the reverse of their current position. In addition, the asteroid and Kuiper belts each have 100 times more material than they do today. The small bodies of both belts are constantly flung around by the giant planets and their intense gravity. As massive as they are, the big planets react every time they toss a planetesimal somewhere else. The reactions may be small, but they add up to make the orbits of the giant planets migrate to new positions.
Early on,